nanohub.org.
Online simulation and more for nanotechnology.
Welcome to the next recitation session for semiconductor device education. My name is Gerhard Klimeck. I'm going to start out again with a home screen of nanohub.org. So we serve students, researchers, and instructors. We have really four major agenda items. We want to enable people to do modeling and simulation. We have now over 700 apps on nanohub, actually. We want to enable people to use those for learning and teaching, and that's the focus of today's presentation. We also want to enable people to develop software and deploy tools within nanohub, and we provide frameworks for that with Jupyter notebooks and Linux workstations, engines, like complicated tools that we will be using today under the hood. And we want to enable people to share and publish the things they developed, including lectures, tutorials, tools, and apps. And those are the main four items that we hope to engage our community with. So under the teaching and learning, you'll find something that we call simulation-powered curriculum. And the idea is that if you're teaching a certain kind of course, you might have a one-stop shop for the things you're teaching. And today, I'll be talking about understanding semiconductor devices. We have a couple of these aggregated tool sets. You click on ABACUS here. If you're in ABACUS, the real goal with ABACUS is to be a one-stop shop for faculty members and students that teach semiconductor devices. So you would typically do things like crystal structure, band structure models, bulk semiconductors, p-n junctions, possibly MOSFETs, bipolar junction transistors, which is what we talk about today, and then MOS capacitors and MOSFETs. So we marched through several of these presentations, and today I want to focus here on this bipolar junction transistor, which is sitting in ABACUS, this tool set. All right, so here's the homepage of ABACUS. As I said, it covers a variety of items, and if you can launch this tool here with a launch tool button, and it'll pop up a tool set here on the screen in a minute. And what you get is a splash screen, so to speak, of this ABACUS, which is really a set of multiple tools that cover, as I said, things from crystal structure all the way to MOSFETs. So today I want to discuss this bipolar junction transistor lab. You can click on these icons, or you can go up here in the tool list and click on this bipolar junction transistor lab. It comes up with two tabs. Here's actually a tab here that includes some homework assignments and explanations about the tool set as well that you can use in your classes. And here is the tool itself. It allows you to look at NPN, PNP, and there's two different geometries. Here's the sort of a linear standard textbook 1D calculation that we typically teach in a classroom. And if you want to have a more realistic, discrete layouts where you actually have a bottom contact to the collector and an emitter and a base, those would be typical 3D discrete components. You can model that as well. So I'm going to start with the NPN linear transistor. And what I would say is, I mean, I teach this in my semiconductor class. I derive the equations for current flow, and I'm going to pull up a slide here that is from my class where I I'm introducing, I have derived the current flow here in the collector and the base. And you have the current gain is the ratio between those two. And this motivates a Gummel plot, which really shows the current that you want to get at the collector versus the base current you stick in to control. And it ultimately allows students, at least in these very simple expressions here, to begin to optimize a transistor, a BJT transistor, where you have the width of the emitter, the width of the base, and you have some material properties, the diffusion coefficients. You have the intrinsic carrier densities in the base and the emitter, and you have the doping in the emitter and in the base. So we can actually walk students through or give them some exercises to look at realistic IV characteristics of these transistors and see how one can improve beta and some of the pitfalls that you might encounter. So let's go in here. So this is a typical structure. You make the collector a little longer. This is, of course, a large device. There's not much quantum happening here. This is solving the drift diffusion equation with a tool set called PADRE, which is an industrial strength tool that comes from Bell Labs. And I'm going to start out with sort of a benign, simple, equal doping transistor as a starting point. So I make all the three dopings of NPN the same, and I'm running the simulation here, and it actually pulled a run from the database of runs that already had been executed. So here you see the doping profile in NPN. You can look at the common emitter output characteristics. So here you see the current voltage characteristic in the common emitter. And so this is the typical thing you want to see. Eventually you see this saturation here. And here is the Gummel plot I had just shown you in a PowerPoint, and you can calculate it also in this tool set. And the ratio between these two currents is the current amplification, the DC gain beta. So obviously these curves are roughly parallel here, and then things are not exactly parallel anymore. So you can plot beta now as a function of the collector current, and you roughly get the amplification of let's look at the number here. So 15, and this is on a log scale. So above 10, not above 20. So what can you do to improve this transistor? And I had shown the slide here that you might also share with your students in your lecture, where there's a couple of knobs you can design in your device. You can change the emitter doping and the base doping. Explicitly, you don't have the collector doping in here, and we'll play with that a little bit. So let's make the emitter doping larger and see what we can achieve. And go in here, and so let's make the emitter larger, higher doped, so 10 to the 17. We can run this IV characteristic again. An issue with do something here real quick. There was something really strange that has happened earlier. I'm going to put in something strange. There's an issue I found playing around where it suddenly wouldn't take the 1E17. It's really strange. I can't explain it. So now it runs this characteristic. I increase the emitter doping. I should be increasing now the current gain. So this is a honest-to-goodness simulation run. It might take 30, 40 seconds, a little bit longer, where it really calculates all of these IV curves and doesn't pull it from a database of results. And now it's assembling the data and starting to plot it. So here you now have an asymmetric doping profile. Here where the emitter is at 1E17 and the base is still at 1E15, and again the collector is at 1E16, sorry, 1E16. All right, so we can look at the common emitter output. So this looks the same. You can compare from before. Indeed, the collector current gets larger. Overall, the curves look quite similar. And you can get the Gummel plot from these curves. So let me turn on the. So now you can see collector current being significantly larger than the base current. You can compare that here. So actually, what you see is making the emitter doping higher effectively reduces the base current. And you can have your students explore why that is in a physical sense by looking, for example, at the energy band diagram at a final bias here, where you can home in onto the valence band here, and you can see how the quasi-Fermi levels and the band energies move, which make the injection of the whole current harder. So it reduces the current, the back injection of the collector, the base current that goes back into the emitter. So you can drive this further, and people have this recipe of wanting to reduce the base doping. If you want to do that, you're going to hit an issue that you may not want to have the base doping be smaller than the collector doping. So let me play a little bit with the collector doping and actually reduce that and see what happens there. So I'm running the simulation again. And there we go. It's not a run that has been done before. So this is sort of really treading on different simulations. So this is not canned. And in a minute or so, we should have the runs be ready. By the way, this is solving the full drift diffusion equation in this PADRE tool. So here you now see a more typical staggered doping profile of 17, 16, 15. And if you look at the common emitter output, again, you see that the turn-on looks quite different now. This is the latest run with this asymmetric doping, where the collector doping was reduced. And you can look at your Gummel plot. And now you see the two running in parallel quite a ways over a larger range of voltages. And also your beta should become a little bit more flat. And then it shuts off here at the high current densities at the saturation area. So we can play with this a little further, where we can increase, for example, the doping here, really make this very heavily doped in the emitter. Let's see what comes out there. I don't think I've run that either. This should still improve the transistor performance. Then the question is what happens on the collector side and the current densities on the collector side. So let's take a look. All right, so now let me go back to my simulation. Common emitter output, that looks actually quite similar to what we saw before here. So you can crank up a little bit more peak current here by increasing the doping more in the emitter. And how does beta look? So beta looks quite a bit improved still, right? So overall, beta, we can crank up a beta of over 1,000. So current amplification of over 1,000. So let's try a bit more, trying to reduce the base doping further and running this again as well. And that might crank up a little bit more current in this design. And I think with that, I'm kind of ready to ask or ask you if you have questions, and I can dive into some other details. It's really your session of sort of a recitation, right? So please go ahead and maybe formulate a question either in the question or in the chat, and I'll be very happy to try to address them.
All right, we have in chat, someone said MOSFET is an extension of BJT.
Yeah, that's exactly how I teach it in my class as well. So to me, the BJT is, in a way, to me, the ultimate example of a ballistic MOSFET. So I pulled up my here. So this is really how I actually introduce it in my class. I have this back-to-back p-n junction where we have basically simple p-n junction equations for the depletion region lengths, and I make them now voltage dependent and show them like this. And in the overview of the course, I actually explained in a pictorial way how MOSFETs work in this form, where I look at it this way: you have this barrier and you inject carriers, and you lower the barrier, you inject more carriers. And ultimately, you have a transistor that opens up, and you have all these carriers flowing in this form. So this is exactly how I motivate the discussion in the BJT.
And we had a little bit of a follow-up to that question. Can we extend 2D MOSFET model to build BJT in the NanoHub tool?
So in the NanoHub tool, that's the discussion for, I guess, in 2 weeks. There is, here in this tool set, there is the whole MOSFET lab where you can design and explain MOSFETs. So I prefer to discuss that in 2 weeks when we focus on that. It's not like you can suddenly make a BJT out of this, but under the hood, it actually runs the same PADRE tool as well. So I saw something flash by on the...
Yeah, we have some questions now in the Q&A. The first one, what is beta?
Beta is the DC current amplification. So let me pull this up here. This is the formal definition here of beta. You have a collector current and a base current. The base current really controls overall the collector current, and the ratio between IC and IB is the amplification that you get in this transistor. So beta DC is IC over IB, and that's the current gain, or DC gain beta.
All right, the next question. Diverging from the BJT module a bit, we offer a course in the clean room with students building diodes and NMOS transistors. It would be great to get to device level models for those structures. Is there a tool in NanoHub that can do fab simulation a la Supreme and interface to device modules?
So yes, it's as you state, it's a bit of a diversion, but indeed we do have process modeling tools, and so let me go to Nano, the homepage, simulation-powered curriculum, and we actually have the oh, it's not in the list. That's bizarre. We have this thing called a TCAD lab, and in there we have process modeling tools as well. I think what we'll do is probably start a new series where we can dive into some of these tools. As this is firing up, so there's process modeling tools that are wrapped around something like Supreme, but it's wrapped around Profit, which is the equivalent from Bell Labs. Let me kill some sessions here. Maybe I'm at the maximum. So while this is launching, there was another question. If you remove BJTs, what topics would you add? Okay, so this tool set is up here. So here we have a couple of process labs like oxidation flux. You can teach students process modeling. If you, so for example, here you can model wet and dry oxidation for a certain time, have model coefficients, and basically what it's doing, it's modeling oxide thicknesses, etc. So some of that can be modeled, and under the hood, it is actually configuring this Profit tool, which is the equivalent of Supreme. And we have this whole tool set here where you can model a variety of things, diffusions, ion transport, p-n junctions, all in this Profit tool set as well. So even a MOSFET here. The issue is it's not an app-like interface, but you have to learn this this language that allows you to model these devices. So it's not quite as appified, if you will, as some of the device tools. But I'm beginning to work with a peer of mine on doing some more process modeling apps that would simulate really tools that are in labs. So students can tweak some buttons in labs, in a virtual lab, and actually run an experiment. But this is not there yet. I hope that answers this a little bit. Now, on the BJT topic, I have it in my class still. But what I ended up doing in my class here at Purdue, which is the fundamentals at the graduate level class, I put the BJTs at the tail end of the course, and I pulled MOS capacitors and MOSFETs into the middle third of the course. And in the last third of the course, I actually let the students design a nanowire, which will be topic in another recitation, where instead of giving them a midterm, I let them do a project on quantum dot design up front and also at the tail end, a nanowire design. And overall, I'm thinking of expanding that more because nanowires as the ultimate MOSFET are the devices that are being implemented today, let it be a nanosheet or a nanowire. So, so I'm inclined to drop the BJT components in favor of a more modeling-based nanowire design experience where students really have a project where they optimize a nanowire transistor in different crystal directions, etc. So that's what I have been doing, and I might push that further. I hope I answered that question.
All right, the next question, does the ABACUS BJT model handle quantum mechanical effects when dimensions are reduced?
No. This is a purely classical code. So PADRE and PROFIT are classical drift diffusion codes.
All right, the next question, could you show an example of the nanowire MOSFET?
Yeah, there is a couple of tools that are not integrated with ABACUS. So there is, and I said we'll have a session on that NanoHub tool/nanowire, which allows you to explore, see these are modes in a wire as a function of gate, and as you crank up the voltage, you open the channel. There are other animations here, where this is the electron density in 3D. Not sure this is not animated. So nanowire is a tool, and then really the true sophisticated tool is Omen wire, which runs a version of NeMo, where you can really have full band atomistic structure, band structure with complicated bands, and you have transmission coefficients, and you have current densities. So these tools are fully quantum mechanical. So this Omen wire is atomistic and quantum mechanical, and nanowire is effective mass but quantum mechanical. So these are fully atomistic tools. Is it? So is it possible to get the slides with the animations just now? We can share the slides for sure. They're also in NanoHub. My lectures are all in NanoHub. So what I just showed you today, we're assembling a NanoHub. That would not work. So here I have my whole course online that includes all the lectures and the material here. And the BJT is actually here in 24. So, yep. So it's on YouTube. You can get the video and you can get the slides. It's all right here.
Okay, great. We have another question. Is NanoHub planning to release any simulation about CMOS in the future?
About CMOS, I think we have a ton of tools in terms of CMOS. I'm not sure. Maybe could you clarify your question? I mean, in terms of individual devices, or in terms of circuits, or maybe I don't quite get it.
Okay, the follow-up to the CMOS is for solid-state storage like NAND or NOR.
So that's more like modeling a circuit element, like a whole gate, I think. And is that correct? I mean, if you're talking about a gate, then I guess the best thing we would be offering is really a SPICE simulation. So you can do run SPICE inside NanoHub. So this would be also, I think it's in this tool set here. Yeah, so you can do, in this TCAT lab, you can run SPICE. So there's a diode AC DC analysis. There's an NMOS amplifier. So those are the things you can model. Yeah.
One more question came in. Can I simulate monolayer MOS2 base transistor?
Monolayer MOS. I'm not even sure I understand the question. Can you elaborate, please? I mean, when I hear monolayer, I think quantum mechanics, right? So here is, I see, my course is here. And this will be also, Amy and I are working on sort of a landing page for workforce development. So my course will be front and center in that as well as other courses on nanotransistors and quantum transport. I mean, that's in the works right now, and it should be showing up hopefully in the NanoHub front page sometime soon.
Okay, a follow-up to the MOS2 question. Can I use 2D material MOS2 instead of silicon?
Not in the tools that I showed, and not, I think, in a tool we have on NanoHub right now. The NEMO 5 code that we developed in my group can certainly handle 2D materials, and we published with it. And I have a student working on creating a tool with that. But as of now, that is not in a tool set, I believe, that I am aware of. But also, I don't know all the 700 tools we have on NanoHub. But I don't think there is a 2D material FET simulation tool.
All right, and that's our last question.
Oh, now I understand the MOS2. It's molybdenum disulfide, MOS2. That's why I got confused. Got it. Great. So thank you, everyone. Thanks for taking the time in your busy evenings. Thank you. Bye-bye.